With the increasing number of Chrysler import vehicles on the road and the success of the Diamond Star operation, it's essential to have a working knowledge of how MMC-built Transaxles operate and how to diagnose and service them. Welcome to this month's VideoTec. In this program, we're going to look at the MMC automatic Transaxles used on Summit and Talon. We'll start by examining Transaxle identification and application. Then we'll prepare for diagnostics by discussing Transaxle operation. Following operation, we'll look at the steps used in diagnosis, followed by a sample problem. On most MMC automatic Transaxles, the identification plate is located on top of the case. On high torque capacity Transaxles, the plate is located on the bell housing. The identification plate can tell you a lot about the Transaxle you're dealing with. The model code represents the type of Transaxle. The number below it represents the build sequence or serial number. This number is important in determining the cutoff points for parts applications. The model code was changed from the old KM designation in 1990. Since we'll be referring to Transaxles by the model code, we need to explore the meaning of the first 5 positions of the newer code. The first position represents drive wheels the Transaxle transmits power to. F signifies that a Transaxle supplies power to the front wheels. W signifies a Transaxle that supplies power to all 4 wheels. The second position signifies the number of forward speeds the Transaxle has. In our case, 3 or 4. The third position differentiates between automatic Transaxles indicated by A and manual Transaxles indicated by M. If the fourth position is alphabetical, it represents the manufacturer. For MMC-developed Transaxles, the fourth position is numerical and represents the Transaxle model. The fifth position further identifies the Transaxle application. The main distinction to make when dealing with MMC Transaxles is between 3 and 4-speed models. 3-speed models, which are used on the 3-door Summit, have an electronically controlled damper clutch in the torque converter, but shifting occurs in a conventional manner through hydraulic valving. On 4-speed Transaxles, shifting occurs electronically. A transmission control unit monitors a number of inputs and outputs and uses solenoids to route hydraulic fluid to change gears. Like the 3-speeds, most of the 4-speed Transaxles also feature an electronically operated damper clutch in the torque converter. Transaxles installed on turbocharged engines, however, do not have the damper clutch. Let's run through the Transaxle types offered on 1991 vehicles. For 1991, there is one 3-speed Transaxle, the F3A21 used on Summit 3-door models. There are 4 4-speed Transaxles. Summit 4-door uses the F4A21. Talon uses 3 models. The F4A22 is used on dual overhead cam naturally aspirated engines. New for 1991 is the use of the F4A33 on dual overhead cam turbo engines and the W4A33 on all-wheel drive models. The F4A33 and W4A33 are higher torque capacity versions of the F4A22. Besides being on the Transaxle, the model number is also located on the vehicle information plate in the 3rd position. The plate is on the bulkhead in the engine compartment. Now that we've covered the types of MMC automatic Transaxles in use and how to identify them, let's review Transaxle operation. At the heart of all MMC Transaxles is a Ravenel-type planetary gear set. This gear set has short and long pinion gears and 2 sun gears. The short pinions rest on the forward sun gear and the long pinions on the reverse sun gear. Power input is through the forward sun gear in first, second, and third gears. The reverse sun gear provides an input in third and reverse. On 4-speed transaxles, the planetary carrier provides an input in fourth gear. The output in all gears is the annulus gear. As with any other automatic transaxle, MMC units use various clutches and brakes to apply or hold parts of the gear set. Let's look at the clutches first. All MMC automatic transaxles contain front, rear, and one-way clutches. 4-speed versions also contain an end clutch. The front clutch controls input to the reverse sun gear and operates in third gear and reverse. The rear clutch controls input to the forward sun gear and operates in first, second, and third gears. The one-way clutch allows the carrier to rotate only one way. The end clutch transmits power to the planetary carrier in fourth gear, but also operates in third gear to provide a smooth transition to fourth. MMC transaxles use 2 brakes to hold and release parts of the planetary gear set. The low reverse brake holds the planetary carrier stationary in first gear, low range, and in reverse. The kickdown brake holds the reverse sun gear stationary and operates in second and fourth gears. Now, let's put it all together by looking at the operating elements as we go through the forward gears. In first gear, drive and 2 ranges, the rear clutch creates an input through the forward sun gear. The one-way clutch allows the carrier to rotate in only one direction. In first gear, low range, the rear clutch operates and the low reverse brake holds the carrier in place. This allows engine braking to occur through the transaxle. In second gear, input is still through the rear clutch to the forward sun gear. In addition, the kickdown brake holds the reverse sun gear stationary so the long pinions can walk around it. In third gear, the rear clutch still makes the forward sun gear an input. The front clutch adds the reverse sun gear as an input. With both forward and reverse sun gears as inputs, the gear set is locked together, creating a 1-to-1 ratio. In addition, the end clutch is engaged on 4-speed units to provide a smooth transition to fourth gear. On 4-speed units, the input in fourth gear is through the planetary carrier by means of the end clutch. The kickdown brake is also operating, holding the reverse sun gear stationary. The long pinions walk around the reverse sun gear, creating an overdrive ratio. MMC transaxles use a number of components to regulate pressure and to apply and release clutches and brakes. Both 3- and 4-speed transaxles use a regulator valve to control line pressure. A separate relief valve guards against excessive pressure. A torque converter control valve regulates converter and lubrication pressure. A reducing valve provides a pressure lower than line pressure. This pressure is used on both 3- and 4-speed units for damper clutch operation. On 4-speed units, the reducing valve is also used with the pressure control valve to cushion clutch application. Now, both units use a manual valve to route fluid pressure according to selector lever position. However, shifting on 3- and 4-speed units is controlled differently. On 3-speed units, a governor, range control valve, and throttle valve position shift valves. This shifts the transaxle from one gear to another. Accumulators cushion the shifts. On both 3- and 4-speed transaxles, a transaxle control unit, or TCU, has the job of activating the damper clutch in the torque converter. The TCU does this through the damper clutch solenoid valve, which regulates application of the clutch in second, third, and in the case of 4 speeds, fourth gear. As mentioned earlier, on transaxles which are used on turbo engines, there is no damper clutch in the torque converter. While we're on the subject of torque converters, note that for 1991, the converters used on F4A21 and F4A22 transaxles have changed to improved torque transfer. On 4-speed transaxles, the TCU controls shifts electronically. For 1991, TCUs used with the F4A21 and the F4A22 transaxles have changed to a 3-connector type. Previous models had 2 connectors. The adaptive shift timing has also been reprogrammed in these TCUs to improve shift feel. Inputs to the 4-speed TCUs include throttle position sensor, ignition pulse, inhibitor switch, transaxle oil temperature sender, AC relay, accelerator switch, kick-down servo switch, overdrive switch, vehicle speed sensor, power economy switch, and 2 pulse generators. The F4A33 and W4A33 transaxles, new for 1991, feature an important difference in the location of one of the pulse generators. In other models, pulse generator A is located on the kickdown brake and receives pulses from the kickdown drum. You could therefore expect a 0 reading from the generator in second and fourth gears after the kickdown brake was applied. On the F4A33 and W4A33 units, pulse generator A is located in the end clutch. As a result, this pulse generator now functions as an input speed sensor. This enhances the self-diagnostics of the TCU. Pulse generator B is located on a transfer gear and, as before, functions as a transaxle output speed sensor. On F4A33 and W4A33 transaxles, the oil temperature sender indicates excessively high temperature as well as low temperature. On other models, the sender's job is to indicate low temperature, so the TCU can modify its outputs accordingly. High torque capacity models have other differences as well. The inhibitor switch design is different, and the kickdown servo switch is larger. On the basis of the inputs it receives, the TCU activates outputs to control shifting. To accomplish shifting, the TCU turns 2 shift control solenoids on or off. The position of these solenoid valves changes the position of the shift control valve, sending line pressure to the shift valves. Here, solenoid A is on and B is off, initiating fourth gear. The TCU also cycles the pressure control solenoid on and off to create a duty cycle. The pressure control solenoid valve works with the pressure control valve to regulate pressure to the clutches and cushion shifts. While we're in the valve body, note that for 1991 on F4A21 and F4A22 transaxles, the neutral drive control valve has been redesigned. This change is aimed at improving neutral to drive shift feel. The new F4A33 and W4A33 transaxles reflect this change as well. Before we end our discussion of transaxle operation, we need to look at a feature of the all-wheel drive transaxle you may not be familiar with. As on the all-wheel drive manual transaxle, the automatic transaxle uses a center differential, viscous coupling, and transfer unit to distribute power to the front and rear wheels. As you probably know, a viscous coupling transfers torque to the wheels on a vehicle which are not slipping. In doing so, it counteracts the effect of the differential. the viscous coupling does allow for some difference in front and rear wheel speeds. The viscous coupling consists of two sets of plates surrounded by a silicone fluid. The inner plates are connected to the center differential, and the outer plates are connected to the front output shaft. When the input and output of the viscous coupling are moving at the same speed, the plates are moving at the same speed, and the viscous coupling does not transfer torque. But when one set of plates begins moving at a higher speed than the other set of plates, the silicone fluid exerts force on the slower moving plates to reduce the speed difference. As a result, during normal driving, when the four wheels are running at the same speed, the viscous coupling does not transfer torque. The center differential distributes driving force. During hard cornering, the viscous coupling transfers a small amount of differential torque between the front and rear wheels. The transfer is so small that it has almost no effect. The torque transfer increases when hard acceleration causes the front tires to spin. When this occurs, the viscous coupling limits differential action by transferring torque from the front to the rear. On slippery surfaces, the center differential causes the torque sent to tires not spinning to decrease. As this occurs, the speed difference between front and rear wheels increases. Here, the rear wheels are slipping. Because of this, there is a speed difference in the viscous coupling, and the coupling will begin to transfer torque to the non-slipping wheels. For further information about the operation of the viscous coupling, see the September-October 1989 VideoTec Eagle Talon Technical Highlights. Keep in mind that although viscous coupling operation is the same, the information in the release pertains to the transfer unit used on the manual transaxle. For more information about the valve body and the electronics in use on four-speed units, see the February 1989 release Mitsubishi KM 175 and 176. Now that we've covered transaxle operation, let's move on to diagnosis. Because of differences in design, there are substantial differences in troubleshooting 3- and 4-speed transaxles. The preliminary steps, however, are the same. First, obtain an accurate description of the problem. Then, check fluid level and condition. The engine should be at normal operating temperature and have been at idle for at least a minute. The check should be made with the transaxle in neutral and the parking brake set. The fluid level should be in the hot part of the dipstick. If the fluid level is low, you'll need to check the transaxle for leaks. When adding fluid, only use a type specified by the service manual and take care not to overfill the transaxle. If the fluid looks or smells burnt, there's an internal problem in the transaxle and it'll have to be serviced. Next, perform a thorough inspection. On electronically controlled transaxles, pay particular attention to the input sensor connections, such as those for the pulse generators, as well as the output connection for the solenoids. If the fluid was low, check the transaxle for leaks. Some leaks, such as those caused by a pan gasket, can be repaired with the transaxle in the vehicle. Other leaks may require transaxle removal. Next, check selector lever and interlock operation. With the key in lock or off and the brake pedal depressed, the shift lever should not move out of park. With the key in accessory, when the brake pedal is not depressed, you should not be able to move the selector out of park. With the key in accessory and the brake pedal depressed, the shift lever should move smoothly. You should not be able to turn the key to off with the shift lever in any position but park. The vehicle should start only in park or neutral, and the vehicle should not move in these positions. Perform a thorough road test. Note the speeds at which the shifts occur and the throttle opening. You can use the DRBII to monitor the throttle opening. At this point, you'll need to use the results of your inspection and road test to decide what the most likely cause is and what your next step should be. The best way to do this is by relating the symptoms to causes, using the troubleshooting charts in the service manuals. You may find that the most likely cause is the engine, the transaxle linkage or its mechanical components, the hydraulic system, or the electronic controls. When investigating causes, concentrate on high-priority items in the chart. These are often the easiest items to investigate. A number of symptoms can be caused by linkage that is out of adjustment. For example, when a vehicle won't start in neutral or park, the inhibitor switch and manual linkage may be out of adjustment. Let's look at this adjustment on an F4A33 or W4A33 transaxle. First, place the selector lever in neutral and make sure the manual control lever is in neutral. At this point, loosen the switch body bolts, then turn the switch body until the holes in the control lever and switch body align. Tighten the switch body bolts to 7 to 9 foot-pounds. Next, with the nut on the end of the transaxle control cable loose, pull the end of the cable to remove the slack. Tighten the nut to 7 to 10 foot-pounds. Check to make sure the selector lever is in neutral, and check selector lever operation. On other units, the alignment of the switch body and control lever is slightly different, but otherwise the procedure is the same. On 3-speed units, a throttle control cable that's out of adjustment can cause a lack of forward or reverse gears and clutch or brake slippage. In addition, the throttle control cable affects shift patterns and smoothness. To check the throttle control cable, with the throttle lever in the curb idle position and the coolant at normal operating temperature, raise the throttle cable cover to expose the collar on the inner cable. Loosen the lower cable mounting bolt and adjust the distance between the collar and the inner cover to about 40 thousandths of an inch. After tightening the mounting bolt to 9 to 10 foot-pounds, make sure the cable can move when the throttle lever is in the wide open position. On electronically controlled transaxles, a throttle position sensor that is out of adjustment or faulty can have some of the same effects as a throttle cable that's out of adjustment. The best way to check out the TPS and other electronic control elements on 4-speed transaxles is with the DRBII and the Powertrain Diagnostic Procedures Manuals. That's the subject of the next part of this program. When preliminary investigation on 4-speed transaxles indicates that electronic controls are possible causes of a transaxle problem, it's time to use the self-diagnostic features of the TCU along with the DRBII and the Powertrain Diagnostic Procedures Manuals for further troubleshooting. The TCU monitors its input and output circuits and stores a fault code when it senses that one of the circuits is not operating as it should. When certain fault codes occur 4 times, the transaxle control unit sets another fault code and enters a fail-safe mode. For 1991, these fail-safe fault codes are numbered 81 to 86. Other codes are numbered 11 to 63. A transaxle that is in fail-safe will not provide shifts. For forward motion, the transaxle will provide only second or third gear. Park, reverse, and neutral, however, will still be provided by the selector lever. The DRBII provides a number of capabilities for transaxle diagnosis. With the DRBII, you can access fault codes stored in the TCU. erase fault codes so that constant and intermittent faults can be distinguished, actuate transaxle circuits to test them, display switch states to check whether inputs are on or off, and monitor sensors to check sensor values. Before hooking up the DRBII or conducting tests, be sure to read the Introduction or Helpful Information section of the Powertrain Diagnostic Procedures manuals. When performing the tests in the manuals, always start with Test 1 or Test 1A, and be sure to perform the verification tests at the end of the manuals. To obtain accurate results, also make sure that the battery is fully charged before performing tests. For checking MMC transaxles, hooking up a DRBII involves connecting the red alligator clip on the MMC adapter to the battery positive post. Connect the other end of the adapter, the 12-way connector, to the vehicle diagnostic connector located under the instrument panel, next to the fuse panel. The 8-way connector on the adapter then plugs into the DRBII cable. For information about using the DRBII, see the February 1990 release of VideoTec 1990 Jeep Eagle DRBII update. Some of the tests in the diagnostic procedures manuals may ask you to conduct pressure tests. Pressure testing is an essential part of MMC transaxle diagnosis and the subject of the next part of this program. Some problems discovered during the road test may indicate that pressure isn't being routed correctly or isn't high enough to do the job. For example, sudden RPM increases during upshift can indicate low line pressure. The troubleshooting guides in the service manuals relate a number of road test symptoms to hydraulic problems. On 4-speed transaxles, before pressure testing, use the DRBII and Powertrain Diagnostic Procedures manuals first to make sure the symptom is not the result of electronic controls. No matter what transaxle you're working on, there are some general practices to keep in mind for pressure testing. You can pressure test by putting a vehicle on a hoist and installing gauges, but be sure to support the suspension at all drive wheels to avoid damage to the CV joints when the drive axles are spinning. For accurate results, be sure to have some way to keep track of engine RPM during pressure testing. Some pressure tests require that the engine be at a specified RPM to obtain a reading. Also, keep in mind the transmission fluid must be warm for test results to be accurate. Pressure test ports on 3-speed units include those for line pressure and governor pressure. The one for low reverse brake pressure located by the dipstick, and the ones for kick-down brake pressure and front clutch pressure located near the pan. The Colt Summit service manual contains a sequence of tests for 3-speed units. Be sure to use the appropriate manual for the tests, since test conditions and specifications may vary. By comparing your results to test result indications in the service manual, you can isolate the cause to the pump and pressure regulation circuit, low reverse brake hydraulic circuit, front clutch circuit, or rear clutch circuit. When the symptom is that the transaxle shifts at the wrong speeds, a governor pressure test allows you to check governor operation. A converter stall test lets you check the ability of the engine and torque converter to provide power to the transaxle and the ability of clutches to hold in gear. The service manuals also contain conditions and specifications for pressure testing 4-speed transaxles. Because of the differences in design, there are differences in location of pressure test ports on 4-speed units. On F4A21 and F4A22 transaxles, the kick-down brake pressure reducing pressure, torque converter pressure, and front clutch pressure test ports are located near the bottom of the bell housing. The end clutch pressure test port is located by the end clutch cover, and the low reverse brake pressure test port is located near the dipstick. On the high torque capacity versions of the 4-speed, the F4A33 and W4A33, the pressure test ports are somewhat different. The test ports for front clutch pressure, rear clutch pressure, torque converter pressure, and reducing pressure are located here near the pan. The end clutch pressure, low reverse brake pressure, and kick down apply and release pressure are located here on the side of the transaxle. If pressures are not within specifications on 4-speed units, troubleshooting charts in the service manual can help you pinpoint the cause. The charts are cross-referenced to illustrations that locate the seal rings that may be responsible for a loss of pressure. Line pressure is adjustable on 3- and 4-speed transaxles. On both units, the adjustment involves removing the valve body. On 3-speed units, the adjusting screw is here. Turning the screw one turn counterclockwise increases line pressure by about 4 psi. Turning it one turn clockwise decreases pressure by the same amount. On 4-speed units, line pressure is the same as kick-down brake pressure. To adjust it, turn the adjustment screw located here. Turning the screw one turn counterclockwise increases line pressure by about 5 psi. Turning it clockwise one turn decreases it by the same amount. You can make 2 other adjustments on 4-speed units, reducing pressure and the kick-down servo adjustment. The valve body need not be removed from the transaxle to adjust reducing pressure, but it's a good idea to remove the oil filter. Turning the adjusting screw one turn clockwise reduces pressure about 3 psi on F4A21 and F4A22 transaxles, and 12 psi on F4A33 and W4A33 transaxles. The kick-down servo adjustment does not adjust pressure. Instead, it sets the tension of the kick-down rod on the kick-down brake band. The adjustment requires the use of special tools which prevent the kick-down piston from turning and allow the correct torque to be applied to the rod. For the kick-down servo adjustment and for pressure adjustments, be sure to follow the procedures in the appropriate service manual. That's the best way to ensure good results. For example, when performing a line pressure adjustment, it's helpful to know the different lengths of valve body bolts, and it's essential to know the correct torque. The procedure in the manual provides you with this information. In the next part of this program, we're going to put the diagnostic procedures we've covered into practice. A vehicle with a 4-speed MMC automatic transaxle is brought into the shop in the fail-safe mode. We inspect the transaxle and confirm that only 3rd gear is operational for forward motion. Because the fail-safe mode could be the result of a problem with the electronics, the best way to proceed is by hooking up the DRBII and using the Powertrain Diagnostic Procedures manuals for MMC transaxles. The directions in Test 1A lead to a check of fault codes. To read the fault codes, we enter the necessary information and then access the Read Fault menu. Fault code 86, shifts points not synchronous, appears, followed by 52, 2nd gear not synchronous. As a result, Test 1A directs us to Test 2A. Test 2A asks us to erase the fault codes and test the vehicle to see if the codes reset. This allows us to distinguish between constant and intermittent faults. Operating the transaxle causes the fault codes to reappear. The problem is constant. As a result, the Powertrain Diagnostic Manual directs us to test 25A, and because fault code 86 is followed by 52, 25A directs us to test 19A. Test 19A will allow us to determine if the problem lies in an incorrect reading from the pulse generator or if the problem is a clutch failing to engage properly. The first step in test 19A is to inspect the pulse generator four-way connector. Check the back of each side of the connector for terminal pushouts or damaged wires. Check connector cavities on the harness side and pins on the component side for corrosion or damage. Next, start the engine and access the automatic Transaxle sensors display. The reading for pulse generator A is within 100 RPM of engine speed, so we go to step 5 of the procedure. Step 5 is a road test in second gear. The road test will allow us to see the relationship between the readings for pulse generator A on the end clutch and pulse generator B on the transfer gear. If second gear is operating properly, there should be a certain ratio between the pulse generator signals received. For the road test, have an assistant monitor the DRBII display. To check second gear synchronization, accelerate at about half throttle with the transmission in second gear. The reading of pulse generator B should increase steadily with that of pulse generator A. In second gear, the reading for pulse generator B should be approximately 40% less than that for pulse generator A. If pulse generator B reads 0 or is erratic, we'll need to check it out using another test in the manual. But if the reading is less than 1/2 that of pulse generator A, but not 0, we'll need to check for a slipping clutch using the procedures in the service manual. Let's assume that pulse generator B's reading is not 0, but is less than half that of pulse generator A. At this point, we need to determine the element that operates in the problem gear. In this case, it's the kick-down brake which operates in second gear. So we need to check the kick-down apply pressure. To do this, we install a pressure gauge in the kick-down brake apply pressure port and check pressure under the conditions specified in the service manual. The pressure reading we obtain is slow to build and below specification. According to the hydraulic pressure troubleshooting chart, low kick-down apply pressure may result from a poor kick-down servo seal or from the valve body. After removing the kick-down switch, we remove the kick-down servo sleeve and piston from the transaxle and find that the kick-down piston seal is damaged, the source of the pressure loss in second gear. As a result, we need to replace the kick-down servo seals and reinstall the piston and sleeve, making sure the ends of the new seal do not align with the oil supply ports. If the kick-down servo seals had checked out okay, we would have had to examine the valve body for loose bolts and sticking valves. After the repair is made, we verify transaxle operation with a road test. From the problem we looked at, you can see the importance of understanding transaxle operation and using a systematic method. With the different systems at work in an MMC transaxle, that's the only way to approach a problem. That's about it for this month's program. See you next month on VideoTec.